Hello, today we're going to be talking about linearization. We're going to find the linearization function L of x of f of x equals sine of x at a equals pi over 6. So what we're going to do is we're going to find the equation of this linear line, this line equation to the curve y equals x squared, or y equals sine of x. And the purpose of finding the equation of this line is so that we can use the line to approximate values close to pi over 6 as opposed to actually trying to evaluate values close to pi over 6. And what we know is we should know the sine of pi over 6. We should know sine of pi over 2. But what about values between pi over 6 to pi over 2? What happens to those values? Well, instead of just guessing what the values are, we could actually use this line equation to approximate values, which you can see is very close to pi over 6. So the process here is we want to find the tangent line equation, because you should notice that this is a tangent line equation, to the function, the curve y equals sine of x at x equals pi over 6. So we have a coordinate there. So the coordinate of interest, or the point of interest, is pi over 6 comma f of pi over 6. So we want to construct a tangent line equation at this point. Let's go a little bit further. So this is pi over 6 sine of pi over 6, because that's what my f is. And this is the same as pi over 6 comma, and then sine of pi over 6 is 1/2. So that is the point at which we want to construct the tangent line equation. Now, in order to construct a tangent line equation, I need a tangent slope. So that means I need the derivative. The derivative is what spits out tangent slopes. You provide the derivative with an x, and I will return to you the tangent slope, or the derivative will return to you the tangent slope. So f prime of x equals the derivative of sine of x, which is cosine of x. And so we want the tangent slope. For the tangent line equation, we want the tangent slope at x equals pi over 6. So that means we want to evaluate f prime of pi over 6. And so that's going to be cosine of pi over 6, which equals root 3 over 2. Again, that's part of the unit circle values that I should know. All right, or the common unit circles, pi over 6 to pi over 3 to pi half, and rotate. And then we also have pi over 4 are values that we should know off the top of our head. Now, to construct the tangent line equation, we're going to use point-slope form. We know that the point is pi over 6 comma 1/2. We know our slope equals root 3 over 2. We got that from the derivative. So putting this together, we get y minus 1/2 equals root 3 over 2 times x minus pi over 6. And here I'm using the point-slope form line equation. Solving for x, I can get the slope-intercept form line equation, which will represent my L of x. So I'm going to solve for y here. That's the process of adding. I'm going to add 1/2 to both sides. And I'm going to distribute. Okay, so I'm going to do two process in this step. And so that's going to be y equals, that's going to be root 3 over 2x minus root 3 pi over 6, and then plus 1/2. And so finally, this gives me L of x, I'll do it right here, L of x equals, so this is the root 3 over 2x, and then combining this, this is going to be plus, so that's going to, I'm going to multiply the top and bottom of this one by 3. Okay. And so that's going to be plus 3 minus the square root of 3 pi over 6. And so this is the linearization of the function sine of x at a equals pi over 6. So if I pick numbers to the left and right of pi over 6, x inputs to the left and right of pi over 6, I can approximate the value or output of sine of x at those inputs. So for example, what we could see from this graph here is that the line is very close to the curve when we're very near pi over 6. But we see that as we drift farther away to the right of pi over 6, the line drifts further away from the curve, meaning that the linear approximation will degrade the further we go to the right of x. And furthermore, when we're to the right of pi over 6, we see that the linear approximation is actually over approximation. Whereas at pi over 6, when we look to the left, we see that the line is below the curve, is above the curve, so that we could see that that's also going to be an over approximation. And the further we get to the left of that, the more of an over approximation we have for approximating values. Now, we know that the sine of x will continue to oscillate. We see that at some point the linear approximation doesn't make sense. If we were to keep drifting further to the right, we would get a linear approximation that gives us a larger output. That would give us something that's bigger than 1. And if we get an output bigger than 1, that is impossible for the sine function, because we know that the range of sine of x is between -1 and 1. So that's where we can start determining where does our linear approximation work and when does it not work. Now, as far as error is concerned, we can find the error of the linear approximation to any value by approximating it using L of x and subtracting that from the actual value of sine of x to get the error.